Good afternoon to everyone here and on Zoom. I want to keep this fairly informal because it's summer and it's the end of July and it's really hot. What I'm saying is that these are 41 slides, a full lecture. Actually, this was my Bagnall lecture at EGU. Hamid invited me to give a talk here the day before I was just about to start vacation after half of it was messed up by my husband getting COVID on the plane to Italy. So then I told Hamid, I'm not going to put a new talk together from scratch completely, but I have the Bagnall medal. So hopefully none of you was at EGU. So maybe none of you has seen it. And so we'll just do it again in a more relaxed setting. But these are 41 slides, so it's a lot. So we don't have to cover it all. It's divided in chapters, so I think we can just stop once in a while, see if you have questions, see if there's anything that you don't understand, anything you want to talk about. So we're not in for a death by PowerPoint scenario, right? It's way too hot to do that. So anyway, so before I get started, there's a lot of people that contribute to the work that I do, and that's particularly my students. So some of them, the ones that contributed, students and postdocs that have actively provided material for this talk are in the first line that you see there. And then the second line, those are all collaborators and people that I work with in those projects at other institutions as well. So when I chose this topic, I almost felt like I shouldn't use the word sustainable in a sense, because it's just such a overly used word. And I'm using this, which is from PhD Comics, and you guys might have seen this before. So essentially there's a ear here. Let me just change into a laser pointer. So we have time axis, x-axis, and then on the y-axis is the frequency of the use of the word sustainable in the English text as a percentage of all words, all right? And so you see data to present day, right? And then there's a projection, as we often do in science, as to what's going to happen in the future. And what essentially this means is by 2100, we would essentially have all sentences that are just the word sustainable if we keep on using the word at this rate, all right? So I am aware that I am going to talk about something that's like sustainable, sustainable, sustainable. And so the question here is, what am I bringing into this talk that is different, that is, meaningful, and that gives to this term, really some meaning that we can use for understanding landscapes and for kind of moving forward into future climate scenarios. So the way I'm going to do this is to essentially ask two questions. And these questions are going to be, first of all, what does it mean for a landscape to be sustainable, okay? And guys on Zoom, I'm going to try to move around, and then if you don't, because I'm really not a static person, but if you don't hear me, which might be the case, I'll come back here immediately. And then the second question is, what does it mean for the people that live on that landscape, all right? And so the conclusion that we're going to reach in a few slides is the fact that these two views, so what the landscape needs and what the people as desire, are very different views. And in fact, I'm going to argue that, and you'll see that coming out, what for people sustainability means is actually stability. And sustainable is actually something that landscapes see in a very different way from the people, from us, that live on those landscapes. So, and this sign that is different is going to mean that there's a conflict here. There's an issue, right, that raises many more issues that we have to resolve. So now, the conflict between people and landscapes, in a sense, or this coexistence of people and landscape, particularly in water and particularly coastal areas, has existed for a long time, and that's because societies by nature establish themselves next to water, right? And that makes perfect sense. You need water because you want fertile soils, you need to fish, you need to think about navigation, energy resources, and so forth. What we also know, though, is that the amount of people that live in these coastal areas has actually increased over time. Okay, Thank you, Sagi. I can't move. And so what you see here in the upper map, this is a study that essentially showed the number of people that live in coastal areas, and that's a snapshot between 1945 and 1954. So the colors go from green to red, and essentially what you're seeing is that the red is the color indicates a lot of people living in those coastal areas. Okay? The snapshot that you have below is another decade, but now it's 2005 to 2012. So even without getting into the numbers or the details or anything else, you see that the map below has a lot more dots that are orange and red, which means there has been an increase of the people living in coastal areas, right? So now all these communities, that are often communities we work with, right, are exposed to a whole suite of stressors. And so you can think of these stressors as chronic or acute. So the chronic stressors are those that happen over longer timescales. So you can think about, decades or centuries. So you can think about sea level rise, you can think about subsidence, you can think about erosion, you can think about river migration. So all these things that are happening over, many years. There's the acute stressors, though, that those are during an event or during a few seasons. So think about an avulsion. Might take centuries before it happens, but when it happens, it's a very acute event. Or you can think about a storm, right? Now, what actually communities experience, often the term that is used is acute on chronic stressors, in terms that you have the ongoing stuff, sea level, subsidence, and so forth, and on top of it, you get a flood event, you get an acute event. As a matter of fact, COVID was in fact often indicated as an acute stressor on chronic stressors, right? That in fact affected those communities, all of us, but particularly those that had already other issues ongoing. Now, the other thing is that these stressors are not just static and staying there, right? The stressors are increasing over time. So these are predictions of sea level rise. And these are done, if you see the legend is pretty small, but essentially you have RCP's predictions. So these are for kind of the previous climate predictions, right, when they were referred to as RSPs, which has the representative concentration pathways. Now in the CMIP 6, they're called SSPs, which I think are the shared socioeconomic pathways. But anyway, what these refers to is various scenarios under which by 2100, you're going to have an increase in radiative emissions in watts per square meters on the surface of the Earth, which would, of course, create other issues, right? So, for example, an accelerated rise in sea level. And so these pathways are, I think I have the 2.6, the 4.5, and the 8.5. So you might have worked with them before. But you can think of them as the 2.6 is kind of like your optimistic scenario, and which is probably unlikely to happen. And the 8.5 is your very dramatic scenario, and the 4.5 is kind of somewhere in between, all right? Now, the point that I want to make here, though, is the fact that regardless of whether you want to be optimistic or pessimistic, which is not really a choice, well, it will depend on what we do, right? The point is that all these curves are actually increasing over time, right? So even in your best scenario, in which we do really well and we control this increase in emissions and so forth, you're still going to look at an increase in sea level, right? So associated with this is going to be also effects on delta loss or land loss in general. I'm going to talk predominantly about deltas, but you can think about land loss. So this is another study that looked at, on top is the observed land area change that happened between 1985 and 2015. And the map below is the projected land area change. Again, this study used the same scenario, so the RCP 2.6, 4.5, and 8.5. Now, I decided to show you the map in between, just not to be super tragic, but that's the 4.5 scenario, and you can see clearly these big dots, which are red, and that indicates a lot of land loss, right? There's very few spots that are green, and those are actually areas that would see land gain. So if I were to show you the 8.5, you can imagine that map is just going to be a series of huge red dots, okay? And lots of this we have already seen if you think about coastal Louisiana. Now, this also means that there's going to be an increasing number of people that are going to live in coastal floodplains, right? So if sea level is going up and land is disappearing, maybe you didn't used to be in a coastal floodplain, but actually now you are in a coastal floodplain, right? And so this is another study that looked at those same RCP scenarios, same thing, but now doing a projection of what is considered a coastal floodplain based on an event with 1/100 exceedance probability or a 100-year return period, and projecting how the number of people would change, so how many people would be living in coastal floodplains according to those RCP scenarios, okay? So again, these lines are all increasing. There's 5 panels, and essentially what this means is the most left one means no vertical movement at all. The second one, you'll notice that the lines are slightly lower because that's a glacial isostatic adjustment, which essentially would bring land up, actually, so in a sense it would be positive. And the other 3 scenarios are scenarios of subsidence in various shape or form scenarios in the cities, subsidence in the cities and in the delta and so forth. But again, this means many more people exposed to those stressors that we were just talking about, okay? This is going to mean also migrations, right? So when we work with coastal communities, we often just think about the coast, right? But actually, these changes are going to impact everyone. So this is a study that looked at changes in population landscape due to climate-driven human migration. So essentially, what you see in colors are counties in the US that would see a change in the number of people that live there. And this change could be in the orange to the reds are counties that are going to see people leaving from there. You see, for example, parts of Florida, right, and parts of the Gulf of Mexico coast, essentially the coasts, seeing a decrease in people. And what you see from the yellow, greens to the blues are counties that would see those people arrive, right? As a fun fact, the most blue spot is actually Austin. It's Harris County, so it's where I'm from, which is going to see like a huge amount of people coming in. But the point is that we can't only focus on coastal communities because as people migrate away from the coast, they're going to go somewhere, right? They're going to move somewhere else, and in that area, they're going to have to find jobs, way to support themselves, houses, and so forth. So this is very much of a global problem rather than, oh, I don't live at the coast and I don't have to worry about it. We're in Alabama, Texas, and we all have to worry about it. But the point is that this is for everyone. Now, there's also going to be changes. Right now, I just talked about kind of the impact on the communities. But of course, river systems, river basins around the world are going to see changes as well, right? So this is another study that looked at changes in the volume and the timing of water delivery to rivers. And essentially what you're seeing is in blue, those are basins that would see an increase in that magnitude of the events, essentially. And in red is basins that would see a decrease in that magnitude. And the intensity of the color is the consistency among the models. So we do know the climate models have, of course, uncertainty, and there's a lot of variability among those predictions. And so these looked at the percentage of agreement between the models. But the point is that you see a lot of fairly intense colors, and you see a lot of the basins in the world that are going to see many changes in that water volume and timing of the delivery of the water, which means we're going to see effects on the sediment transport and effects on the ecological function of those basins, right? So now, the last piece I'm going to add to these scenario here is the fact that human intervention. So if we think about, I'm trained as a civil engineer, and flooding protections are something that make a lot of sense, right? So you have communities, you got to build ways of protecting them. Now, the problem is that long-term, those actually create often more problems than the problems that they were supposed to fix. So this is an example from Bangladesh, which is one of the landscapes where I worked a lot. And essentially, polders, this is a Dutch term you may be familiar with. It indicates an island, essentially, that is embanked, right? So a landmass that is embanked. And it's the Dutch essentially brought the embankments in Bangladesh in the 1960s. And since then, these lands have been embanked and people leave behind these levees. Now, some of these embankments are, as you see here, fairly structured. Some are actually more like, much more temporary. But the point is that there's a plot down here which is quite complex, but actually I just want you to compare the right bank here, which is essentially the part that imagine is pristine, which is the mangrove forest where the rivers can move, and then things can pick up, and sediment can be accumulated, and so forth. And the left side here, which is the side where the embankment is, right? And so what happens with the embankment is what we can refer to as disconnectivity of the river and the floodplain. So essentially the idea is that you're preventing flooding, great, you're protecting people, but what is the problem? The problem is that the river is not only carrying water, right? It's carrying sediment. So if you put a wall there and you don't let the river expand, the sediment is just not going to reach the floodplain. If it doesn't reach the floodplain, you don't have any aggradation of sediment, but the land keeps on going down because you have natural subsidence because of compaction, but because also you're extracting water, you're extracting energy resources, and so forth. So this creates a situation like in Bangladesh where the elevation inside these polders can actually be a meter below mean high water, which is a lot, right? So you're leaving behind a wall, but the moment that wall fails, which has happened, as in Cyclone Isla a few years ago, then you have thousands of people displaced, people dying, and also places where they're going to stay inundated for many, many years. Now, I'm not going to get too much into this story, but it's actually a silver lining here, because when Cyclone Isla caused one of these embankments to fail, lots of the sediment got in. And actually, there was a lot of aggradation, which suggested that if you reconnect the river and the floodplain, you could, in fact, contrast this land loss, and you could aggregate, in fact, sediment on the floodplain. But there's a huge social problem of where you're going to put the people, right? How are you going to tell people that they have to move? They have to be gone because you periodically have to flood this area to aggregate it. So it's a very complex social problem on top of being like scientifically, problematic and interesting. This is one example. Another example that I'm going to show you is closer to home. So this is the Mississippi. So this is a study that it's actually, again, I'm not going to go into details, is again a very nice paper in which they did a whole analysis to reconstruct the paleoclimate. So they went back and were able to reconstruct the storm patterns, down to essentially 500 years ago. And what these allowed the authors to do was to say, can I explain the intensification that I've seen in the frequency and the magnitude of the events? Can I explain it based on climate? And climate changes in climate. And essentially what they saw through modeling and so forth is that the blue line is what you could explain according to climate. But the observations are up here, which essentially means, again, the levee system that we built on the Mississippi, very reasonable from a perspective of protection. But what has happened is that has caused an intensification of the flooding event. So again, protections that you put to save people, which also create problems because people will live close to the floodplain, in the floodplain that they shouldn't. But the point is that these interventions end up creating an intensification of these events. So it's a side effect of lots of these interventions that we placed, in fact, in the mid-1900s. Last example I'm going to show you is from the Venice Lagoon. These are very recent papers that came out between last year and this spring. And essentially what these authors did was they had information on marsh aggradation, so sediment accumulation in the marsh, through time. And this is essentially a snapshot from late 2018 to January 2021. Now, what you're seeing here, the bars that you're seeing here are the sediment accumulation measured in the marshes. And if you notice, there's like these little clouds with the thunder. That's when the storms happen. So you can see that through time, when there's a storm, often there is like this peak in the sediment accumulation because, again, the sediment comes in because Venice essentially, sees these large events coming in. Now, the thing is what happened here. So the MOSE system, again, a flood barrier protection was put in place to protect Venice from flooding. But the problem is that the moment the flood barriers became active, which is right here, what you can see is that you have storms and you barely have any sediment accumulation, right? So this means that what they concluded is just 15 barrier closures. So we're just talking about data from October 2020 to January 2021, which is almost nothing, right? But just in those 3 months, they saw they could attribute the 12% reduction of marsh deposition due to the barrier closures. And then where is the sediment going? Well, this sediment is staying in the channel. It's causing channel infilling, and then there's other problems because then you gotta dredge this sediment and so forth. So it's kind of messy, right? So you've seen that there's this interplay between what we're trying to do and achieve and what the landscapes do, which leads me to the point that from a people perspective, what we want is actually a preservation of what's existing. So often what we're trying to achieve is stay as you are, don't move, right? Because we need to live here, so I can't afford having river migrations, shifts, avulsions, or things like that. But so this essentially brings us to make interventions that really prevent those shifts in location, so the river movements and so forth, which are actually needed for the dispersal of the water and the sediment on the delta plain, right? There's no other way to feed the landscape really other than letting the rivers move. And so you're modifying the network dynamics, right? You're preventing the movement, and as you saw in some of the examples that I showed you, this often leads to worse events that we actually saw before. So from a landscape perspective, then what actually the landscape want to achieve in terms of sustainability is actually a persistence of the landforms, which comes with preserving in a way their physical functioning. So they have to be able to shift in location. They have to maintain this water and sediment dispersal. And this is clearly in conflict with this need for stability that communities have, okay? So that's the first point that I want to make. If there's anything you have to take out of this lecture, just remember this part. Then I'm going to get into possible things that can help, right? But certainly there's this conflict. Now I'm going to push it further, and I'm going to say this conflict is actually more than this. It's a conflict of scale. And I'm going to make this argument in two ways. First one is the fact that we often assess systems at a global scale, right? And I do that too. We do remote sensing studies. Well, you'll see some global studies in my presentation. We kind of look at things from above and we say, okay, these are the patterns, right? Well, you may conclude, so if you look at the Ganges, for example, and you ask the question, all right, so how much sediment do I need to keep up with sea level rise, and do I have enough? You do, because there's this humongous amount of sediment coming in. And so essentially the delta, from a mass balance perspective, you could say, okay, I'm going to be fine. I'm going to be able to keep up with sea level rise for the next century. Now, what is the issue? That sediment is coming in, and what is the sediment doing? Is it a uniform distribution? What do you guys think? Is it uniformly distributed over the landscape? It's not, right? So you're going to have areas that see a lot and areas that don't see much. So what this means is that if you have your global view, which is helpful in some cases, you have no idea what's happening locally. So you can have a system that, from a mass balance perspective, has enough sediment to keep up, but then you look locally and you're saying, well, that view really doesn't have anything to do with what my community is experiencing right here, right now, over the last decade or so. Now I'm going to flip this argument and say, when we think about solutions, we think very locally, right? So I just made the argument that the global view doesn't have really a point in representing what's happening locally, because this distribution of fluxes is not uniform. Same argument of scale, but the opposite ways for solutions. When we think about solutions, we often think locally. So you'd be like, okay, I'm going to put a levee right here, right? But that is actually going to be problematic because the process that you're trying to mimic or replace, for example, to deal with, is a process that happens at the system scale. If you think about an avulsion, the nodes are much more upstream. It can sweep the whole system. So what is your local levee going to do? Nothing. So now this is an issue because a system scale management solutions or strategy is very hard to achieve. I think politically it's going to be a nightmare, right? Money-wise too. So you have this discrepancy in which we often do analysis globally and we don't think locally. But when we do solutions, we are local and we don't think about the fact that the processes they were trying to replace, they were preventing from happening, are happening at the system scale. And so your small levee in a local condition, besides the fact that it has effects to those downstream and upstream and so forth, but also there's an issue, right? So that's why diversions, we started thinking about diversions because they could, in fact, do more system scale approaches, but again, difficult to implement. So where am I going with all these issues? So what I'm going to do, I said I was going to talk about sustainability in a different way, or at least in the way I like to think about it. So I want to show you essentially 3 examples, and as I said, we don't have to do them all, but ways in which I think we can help. So I don't have all the solutions. I don't. I mean, we don't have any solution, actually. But what I can do is to say, what can we do as scientists leveraging all the tools that we have, because we are at a time in which there's actually a lot out there, right? We're getting more remote sensing data, we're getting more modeling capabilities, we can do more field and so forth. So what is the information that I think we can provide that can help in informing this type of analysis, right? So what information can we provide to communities, but also to landscape managers and so forth, and say, all right, these are ways in which we can help, all right? And so I'm going to show you 3 parts. And it's going to be, first of all, measuring hotspots and rates of change. So can we tell where the systems are changing the most? And can we tell at what scale are they changing, right? I want to show you then how we can estimate flux partitioning. So again, I was making the argument that global to local misses the fact that the fluxes are not distributed uniformly at all, right? It depends on the network. And so I want to show you cases in which we can leverage the network information to estimate the flux partitioning, okay, of water and of fluvially transported material. The last part, if we get there, it's going to be looking at trajectories of change. So in thinking about what's going to happen in the future, leveraging modeling, and thinking about, acute and chronic stressors, okay? You guys feel like it? You're going to make it? Any question or any comments so far while I drink?
Positive stories. Up to this point, the entire motivation is
dramatic.
Yeah.
I think there are. I think the positive is what we can do. I think there are. So the question, if you guys didn't hear it, is, I've been fairly. I try not to, but I've been fairly dramatic. So is there any positive side of this? So I think, I'm not going to get to climate pathways and things like that because we know where we're at with that. But I think from a science perspective, we have way more data and way more tools than ever, right? Those keep on increasing. The question is how we're going to use them. So I think we do have the capability of bridging the gap. And that's kind of like how I got interested in networks and how I became more of a person who thinks about networks, because I do see it, for some systems, because then you could say, well, there's systems where there's no network. Okay, that's fine. But, for systems like the Ganges, for example, or other systems, the network is really responsible for that scaling down, right? You're going from the inputs, how do you get to the local information? Is through the distribution, through the network. And I think we can actually monitor that or measure those rates much better than we used before. So I think the positive is that from a science perspective, we do have possibilities to do something and provide data and make things available that can help in taking those decisions. We can't necessarily, change people's view or make governments do things, but I think we can provide the data that I think is needed for taking those decisions. So I'm going to start talking about hotspots of change and migration rates. So we're going to be working with time series imagery here, and predominantly it's going to be Landsat. And most of this work was done in 2 dissertations. So Leo was a former PhD student of mine that was an electrical engineer, so he did a lot of the image processing work that I'm going to show. Tess was a PhD student of mine. They did the application of those tools for Delta system. And then Austin is a postdoc that I recently worked with, who also did some of these applications. So you'll see all of them represented in the next few slides. So I've done a lot of, sometimes when I give these lectures, I also put a plug for open source. Everything I have done since I was a student has been publicly released as open source. I'm a huge supporter of open source. So as I go through the slides, you'll see a lot of these teal links. Links in light blue, those are all GitHub repository or data repositories where you can take all the codes and do things with them, and hopefully also contribute to them. I do think that the landscape is great these days for open source and for contributing to open source tools. So keep an eye on those and try and break and do whatever you like. So because we wanted to work on landscape on networks, we have spent a bunch of time thinking about extraction of networks, right? And there's a bunch of tools out there, so these are the ones that we have developed, but no tools is perfect, and there's always room for improvement. So the first thing that you need to do is usually to extract a water mask. So this is one of the tools that we developed. This is Deep Water Map. It's a deep convolutional neural network approach, and essentially takes a Landsat image. In this case, it's a Landsat 7. But you can put pretty much anything you want in there. and then essentially outputs surface water probability. It's actually not exactly binary, but it's a map of where the water is, and actually this does a very nice classification, so it will tell you, will classify clouds and ice and shadows and things like that, and get you out a map of water. So then from there, you need a network extraction. Again, we've done multiple tools. This is one. Different approach than before, because machine learning is kind of like a black box, so sometimes you don't know what's really in it, so I wanted to show something else. This is a handcrafted filter, essentially, that you see here. It looks complicated, but it's not. So essentially what this is, if you think about landscapes, we often get topography, which is data that we're often used to work with. We often get information from slopes and curvature, right? You get curvature, you get slope, you know where the channels are, you know where the slopes, where the banks are. Same thing here, but this is done on the intensity of the image. So these F0, F2, and F1 indicate the order of the derivative. So essentially, you have a first derivative at the bottom and a second derivative at the top, which means you're going to favor the extraction of those regions that have high curvature, and you're going to ignore as much as possible the regions where the gradients are sharp, which means the edges. This is because we were after center lines, so we wanted to catch the core, the center of the channel. If you want to get the banks, you would do something completely opposite, right? And the rest of the stuff, the fancy stuff that is here, is because the derivatives are directional. And also, when you apply these tools to landscapes, to channels, there's a lot of scales involved. And so the sigma indicates an analysis is done across scales. So we go from the smallest channel scale to the largest channel scale. And then we compact this, and we get the highest response of the filter at each scale locally. So the scale that gets maximized locally. So this does a nice job, and it gets networks out, okay? This has nothing to do with changes over time. So this means that you got to go to a time series. So this is work that the test did, and what we did was to say, okay, so let's say now I have multiple images. This is synthetic, of course, because it's easier to test things on synthetic data. So imagine you have this delta over time, and what you can do is to extract this information with the filter at each time step. And then you can check how things have varied over time. So imagine you have a situation like the top, in which you have these 4 channels here, and then if you check what's going on as you move right, the top, the feeder channel remains the same. The channel on the left is enlarging. The channel on the right here is shrinking, and this little tributary channel here has actually disappeared, right? So this is the filter response. And then what we want to do is to do this analysis over time to get the variance, right? So I want to see how much these areas have changed. So if you focus on the map on the left, this is a map of variance. We call it CRV, it's the channelized response variance. So this tells you nothing happened here, and it shouldn't, because the channel remained the same. And the highest variance is here because the channel actually disappeared, right? But these, as you see, doesn't make any distinction as to whether I'm enlarging or I'm shrinking. But I actually want to know that because I want to know if water is appearing or disappearing. So what we do, and what leads to the result on the right, is that we do a linear regression over time. So that way we can tell if things are just fluctuating back and forth because tides change, discharge changes, we don't care. But if things are on increasing trend or decreasing trend, then we fit that, and we essentially assign a sign to that variance. So essentially, when things are in red, they're negative, which means the water disappeared from there. So think about a channel infilling. And when the variance is positive, it means that the water is appearing. For example, a channel is expanding, right? Or an area was land and became water, okay? So this is what we do in synthetic data. I'm skipping all the validation of this, which we did on experiments, because again, it's pretty much impossible. Or it was impossible for us to test things on satellite. So we had the results on satellite immediately. We wouldn't believe them. We went to the experiments, we tested it, we validated the method. We're like, okay, we can believe them. We went back to the satellite. And so these are the results, for example, on the Ganges. So you get these maps of red and blue. As I said, the red is the negative. So this is water disappearing. The blue is positive, so it's water appearing. So of course you see a lot of action in the braids because these rivers are very dynamic. There's also interesting things that, in terms of positive things, for example, there's points that don't move. So that's important information for communities. There are actually node points that are not moving over time. But the other thing that is super interesting is this discrepancy that you see better here between this area and this area. So now these are the mangroves, and this is the area of the polders. So as you see, again, areas embanked, you see a lot of these red, that's all channel infilling. That it's happening again because you're preventing that expansion into the floodplain, and the channels are just infilling. There's a lot of other problems. So we do see a signature of anthropogenic modifications in Landsat, and this is just over 30, 40 years. So lots of the results that I'm going to show you are over human timescales, right? So these are all things that you can experience as you live there. So now, these are just hotspots, all right? So now how do we get to migration rates? So what we thought about doing is to use PIV. So particle image velocimetry, you may have heard about it. Maybe if you have a colleague that does fluid mechanics, experimental fluid mechanics especially, or sometimes you see it online. So what people do is to use PIV to measure instantaneous velocities from experiments. So you shine the light, you follow the particles, you measure correlation between images, and you get instantaneous velocities. It's also very nice to just visualize patterns, so you can see all these turbulent structures and so forth. What does that have to do with channels? Nothing. We just thought we could use it. So we took PIV from experimental fluid mechanics and applied it to center lines, all right? And so what we did is the following. If you see here, maybe you see it. So the red, actually the blue is the earlier center line. So this is 1986. This is a piece of the Amazon. And the red is the 2017 center line. So what PIV then does when you apply it is to track one center line into the other one. And it gives you a vector that tells you in which direction and how much that center line became the other one. Okay, so we're going from the beginning to the end. There's discussions that we can have because this is Landsat, it's 30-meter data, so we don't go year by year or month by month because we can't do that, but we can go over the whole Landsat, amount of time. And so we get all these migration rates, which are great information. And so then what we do, global, and I declare this is global, so there's a lot of simplifications. What we did was to take those migration rates over the delta and do an average for the whole system. Again, this is global, so we know this is not necessarily representative, but this is interesting because you can link those average migration rates to other things. And so, for example, you see that river dominance, large sediment input would lead to higher migration rates. The tides and the waves are usually stabilizing, so those rivers don't move as much. And the other thing is that, again, these migration rates have been experienced over the Landsat record. So we're talking about 30, 40 years, right? So human timescales. And this is also interesting because then you can think about those climate predictions that I was showing earlier and say, okay, if a system is moving this much and now I'm going to see this increase in discharge, what's going to happen in terms of migration rates, okay? So the other thing is that there's this global data set, so we have all these rates that people can map and see. And they're also very local, so you can start comparing, for example, we did this in the Ganges, what happens in one area versus another one, where is the larger migration, where is migrating less. Again, this is information that you can give to communities because those are changes that they have actually actively experienced. We have done this also with experiments. So in this case, this is what Austin did. And what he did was to instead use PIV not for the center line, but for the channel banks. So that's a super interesting topic in itself because channel banks, we know they don't move in a symmetric way, so they move at different rates. So you can track what's happening in an experiment. And in this case, for example, we were able to say there's more erosion, then there is bank accretion. And so we started explaining some behaviors that we see in braided channels that we can explain in terms of what the threads are doing in the experiment. So it's a very powerful technique, is very helpful, and it kind of gives you information that we didn't have before of how much these rivers are actually moving. Okay, end of the first part. How are you guys doing? Yeah, go ahead.
Okay. I want you to take us back to the Ganges.
Yeah.
I know a little bit, and years before I actually walked some of those places and measured balance centers. Okay. I wonder, with all these fancy tools, if I were a Ganges floodplain manager, why would I call Austin and give you some money, and what is the added value you would bring?
Because you want to give me money? Because otherwise I would give you all this.
I know. Being a faculty member, I would do the same thing. Right? But to my boss, if I'm a floodplain manager, how would I justify that? I mean, first of all, labor is cheap, right? I can always send somebody to find out is the channel disappearing.
Yeah.
I got local, right?
Yeah.
And there's a ton of information. It's a very populated area, especially
I've been there. Yeah.
You can call people and they'll tell you.
They know what has happened. Yeah.
So what is the added value of these fancy tools for, say, Ganges? Could be valuable for some other place, which is remote and very few people.
Yeah.
In a highly populated area like this, what is that?
Yeah. So So the question, I'm not sure you guys hear it, is essentially what is the added value of these tools in a landscape like the Ganges, where you have so many people living there that effectively you could get local information on what's happened. Is that fair enough? Okay. So I think, first of all, yes, you have a local information, but I think it's very hard to have it simultaneously everywhere, I think, first of all. The other thing, so you have in this map, and the other maps of the migration rates, if you want, you have a system view, and you can actually zoom in. And first of all, there's no money to be spent, actually, because all this data is publicly available. So you can just take it, all right? So there's actually nothing on the Bangladeshi side that they would have to do. Now you could say, well, there's more data coming out, so I want to update these maps. Then in that case, you can run things and whatever. So I think one of them is the fact that you have this simultaneous information, in one in a huge delta, as you know, which I think it would be hard to collect. It's objective. It can be checked with people living there, but at the same time, you are applying the same criteria over the whole system. While if you go by local experience, the truth is that what one community may call a problem, another community may not, and so forth. And then the other thing is that I'm showing you a snapshot in time, but I think the powerful thing to do would also to do this in increments of time. So you can say, when is the system more active? For example, the migration rates that I was showing, from a geomorphological perspective, it's very much of a push, because what I did is to take 30 years of change and then divide it by 30 years and say, this is the amount that it changes per year. That's not the way it works, right? It's going to move more or move less, but you can do this in more detail. So I think it adds information to the sense that you have a map, and for example, you're doing field work, let's say. This was a project that we had with a bunch of colleagues. It was a coastal seas and a self-funded project, so I had colleagues at LSU and colleagues at Vanderbilt that did the field side. And for example, they had to decide, where do I go in the field, where shall I take samples? Because you can't go everywhere. They use, for example, the hotspot map to say, I can go sample these different areas because they're actually showing a different behavior over time. So I think from a science perspective, it does give you this snapshot of the system over time. From a community perspective, I think what you have is an objective way of measuring the whole system rather than pockets of information here and there. And it's very hard to do simultaneously everywhere, right? Even when you go measure things, you can't be everywhere at the same time in the same conditions, right? Because you usually have one boat, one thing, 3 instruments for sediment. We're always limited. So I think that's where remote sensing goes. I don't think remote sensing substitutes the local information, but what it does is that allows you to calibrate on a smaller area and then say, okay, now let me take the whole system view and let's see what happens. I didn't convince you, did I? You're not gonna give me the money. All right, so can we sneak in another chapter? How are we doing with time? Yeah, go ahead.
I just wanted to let people know that are taking photos of the GitHub link that we are recording it and we'll share it on.
Yeah, and it's all actually, it's not all my GitHub repositories, but they're all also linked from my website. How are we doing with time?
It's 4:20.
Okay. Maybe I'll do another chapter. Yeah, I'll do the second chapter. Tell people start leaving. Don't let me talk forever. All right. So we're going to talk about flux partitioning, okay? So I made this argument that fluxes are not partitioned uniformly over the system. So the question is, can you make an estimate of how they're partitioned over the system? So we're going to start when this is work that Kyle and Jay did. So Jay did the more remote sensing side that you're going to see first, and Kyle did the modeling side, which you're going to see next. Both graduating in summer. Dave, you just missed 40 minutes of presentation. I would start from scratch, but I don't think they would want to. But you can get the second chapter and just starting. All right, so I'm going to show you first what happens with remote sensing. So one thing that we often do, you may have done it, or other people that you know may have done it, is to say, okay, I'm going to think about discharge being partitioned based on channel width. If you look at the network and you have the width is easy to measure from remote sensing because you just need surface information. And often what we do is to partition the water, saying it's going to go as width, right? But the question that we ask, and that Jay was interested in answering, is, is that good, right? Can we actually say, what error are we making in just splitting by discharge? Or is there a better way to partition this? So the answer is going to be it's actually quite good. So we're using another open source tool that I did not develop. My student developed with John Schwenk. So it's called ReefGraph. What ReefGraph does is it takes a water mask and then it shrinks it to a network, and then it will build essentially a nodes and links network that also, assuming that all the flux, that there's no tides, assuming it's a stable condition, it will also give you flow directions along the network. So essentially what we do is that we use ReefGraph to get the information on the network and the width. And then we collected data from what we could find in the literature of where people had measured discharges, right? And we found data from 15 delta networks. This was in the literature, so we collected these things, and we have discharge data in 162 channels where the measurements were made. And other data was partitioning. So at 46 junctions, people would say 40% goes this way and 60% goes that way, right? So we did the estimation with our method, and then we compare the estimation from remote sensing with the estimation done in the field, right? And we measured essentially 3 metrics of error that you see here. The first one on the left is very basic, so it's just the difference between what you measured based on the graph and what you measured in the field. The second one is that error, but normalized by how much discharge is actually measured in the system. And the third one is the error at the bifurcation. So it's essentially measuring, how good you are at estimating the partition, the asymmetry at the bifurcation. So in all these cases, you will see that these distributions are actually quite nice in terms of they're centered around 0. The bounds are not very large. So the truth is that the error that we make in estimating discharge by width is actually quite small. I mean, it's not terrible. We're actually doing quite good. And there have been other approaches proposed in the literature, for example, width to some exponent, or you could think about, shall it go to some exponent, which has been, done in the literature. But the truth is that at this scale, at least on many, many, many systems, width itself is just fine. So it's a pretty good estimation, which is great to hear because you can get a good idea on discharge just from remote sensing. Now, this is water, right? We're not only interested in water, but also interested in stuff that travels in the water. Now, things here get a little bit more complicated, right? Because water is one thing. So what we did then was to develop a model or a tool that is called Dorado, and you're seeing results from Dorado simulations here. So Dorado was my dream for many years, and I stressed my students about it. I kept on saying until some of my students really picked it up and did it, which is it's essentially a hybrid approach. So it's a Lagrangian transport model that will track particles through a system. So it sits on any hydrodynamic solution that you have. So you solve your hydrodynamic, you do your hydrodynamic model in the way you want, and then you'll inject particles in the system. You can track these particles. Now, the reason why we wanted this is because we were after residence time distributions and things like that. So I wanted to understand where the particles go, how long do they take to get there, and how long do they stay there. So I needed a Lagrangian approach because I wanted to follow each and every particle. The example on the left is a project that we just started on the Trinity River, which is a meandering system. So again, we're looking at floodplain inundation, river floodplain connectivity, and where the particles go under what conditions and so forth. The example on the right is what I'm going to focus on here. This is Louisiana, and actually the system on the left of this map, this is the Wax Lake Delta, and this is the Atchafalaya. So this is one of the few areas in Louisiana that is actually growing land. The reason is this is also an engineering mistake in a sense. It was a flood diversion. It was a diversion done to control flooding in Morgan City, which ended up building land. So then it became subaerial about 40, 50 years ago, and it built at about 100 square kilometers of new land. So we have used this system a lot as a proxy for what we might see from river diversions. Now, the reason also I'm going to focus on this system is good because it's a very good system to ask the question about connectivity of materials other than water. And the reason is because we spent a lot of time already in understanding the connectivity of the water. So when we started working on the system was 10 years ago, and we're like, oh, we want to understand connectivity in the system. So how much water goes from the river into the islands, And I thought, this got to be easy. I mean, it's got to be straightforward. It's just water. What's the problem? First field campaign we go and measure what's coming in terms of discharge. We measure what's coming out, and my student is like, we're missing 50% of the water. And I'm like, no way, we're going to go back and measure it. We go back and measure it. Well, sure enough, 50% of the water leaves the network, so it's a leaky network, and goes into the wetlands, right? And so that means that all these network approaches that I talked about, well, they're a little challenged because this system loses water. They're leaky. The network is actually leaking water into the wetlands, and the wetlands then are transporting this, which is great that they do that because there's also sediment that goes there, right? So we know the water here really well. And also there's this beautiful NASA mission of which I'm part of their science team. It's Delta X, and Delta X started a couple of years ago. And what we're after is controls of aggradation in Louisiana, soil accretion really. So we're looking at the network role, the vegetation role. And so we have these fantastic new instruments available, which are prototypes of future NASA missions. So we have air SWOT, which is on a plane. So these are all on a plane, but air SWOT is a prototype of SWOT, and NASA's SWOT mission is about to start in a few months. We have UAV SAR, which is a prototype for NISAR. NISAR is going to start in 2023. And we have AWI NG, which is instead doing sediment concentration and vegetation mapping. That is a mission that is not mapped yet by NASA, but it may happen in the future. So we had these great instruments, somewhat similar to what's going to be on the satellite, higher resolution though, and higher passes. And so the beauty of this is that these, so I'm in the science team responsible with Sergio Fagarazzi for the hydrodynamic modeling. So there's other people for other parts. But the point is that we're mixing, it's a whole interplay, right? So there's no tool that does everything. So we were in the field collecting information at the same time as the planes were over our head. And then we're using the model. So it's model, remote sensing, and field all interplay. And the other thing is that, again, everything is public. So you see it here. So NASA is actually applying to Delta X the same rules as for Landsat. So the moment I show you something in a presentation, it means that that's already available for download. So keep in mind that all the Delta X data is available to everyone. So we wanted to, so going back to the original goal, we want to understand the transport of materials other than water, right? So I'm after, for example, sediment or nutrients and so forth. So we're using the capability of Dorado then. And as I mentioned, Dorado, it's Lagrangian transport. It's actually inspired by another model that is in my third chapter that you're probably not going to see, which is called Delta RCM. And Delta RCM is a model for creating and evolving a delta. It's essentially a delta formation model. These models are reduced complexity. So we're not actually solving the shallow water equations. We're not, it's rule-based, right? So it's very simple in a sense. It's a weighted random walk. So essentially, it's random, but not entirely. So you're still using physics, and the rules mimic the physics. So essentially, in Dorado, which uses the same things as Delta RCM, the weights are controlled by two parameters, which are gamma and theta. Now, the gamma essentially is a diffusivity parameter, if you like. It will control, if you like, it weights the flow directions, either flow velocity or the water surface gradient. And you can give weight more to one or the other depending on how confident you are with your hydrodynamic solution. The theta is what you see right here in the equation for the weights, and it's right here, and it's the exponent of the depth. So that means what? That I can actually model a whole range of materials and say, okay, well, if I'm a surfactant and I'm on the water, for example, I'm pollen or something like that, probably I can't care less about the depth. But if I'm sediment, I'm more likely to go towards deeper water and be transported by deeper channels. And so in this case, I'm going to have an actual dependence on depth, which is to the second power, right? So we play essentially with theta from 0 to 2 to essentially go from stuff that is on the surface, water that is a theta equal to 1, and bed load material that is going to be transported towards the bottom with a theta equal to 2. Now, I'm not showing you the validation of any of this, but we did. So we did some back calculation with Rouse profiles and things like that, so it's not unphysical. But it's convenient because it's a reduced complexity framework that allows you to transport materials in a sense. So what I'm going to show you then is results of connectivity, but for this range of materials. So this is a busy slide. And what you're seeing is connectivity, or actually is nourishment. So you can think about the intensity of the color indicates what fraction of the incoming material it's going through that location, all right? So what fraction of, you have a bunch of stuff coming in, how much of that is passing through that location? We think about nourishment because if I'm a gradient at a certain location, it means that I'm receiving sediment at that location. So we're mimicking that. Now, the first column is the theta 0. So this is the distribution, if you like it, the partitioning of the stuff that is on the surface. The middle one is the theta equal to 1. So this is water. And the right one is the bedlow material. Think about the theta equal to 2. Now, the 4 rows are essentially steady conditions, so no tides with low and high discharge. And below is tides, so unsteady conditions with low and high discharge. Now, you can see, we can talk about it. You can see the tides are mostly effective for the stuff that is on the surface, not as much for bed load. But the point that I want to make here is that these 3 columns, I think we're all agreed, that are very different, right? And so you tend to have heavier material in the channels, which probably you would expect it. You tend to have surfactants very much distributed into those wetlands. And the water is something in between. Now, why is this important? It's because we often think about other materials, they go by water, right? So you say, oh, I have an idea of hydrological connectivity, I know where the sediment is going. What essentially this is telling you is that if you assume the sediment is going to follow water, well, you're actually overestimating how much sediment you're going to see in a given location, because the connectivity of the sediment is very different from the connectivity of the water, which means we got to go out and measure it, right? And there's actually remote sensing ways of doing that too. So this is another way of seeing the same thing, and essentially that is each area, it's nourished by the max by which theta. So essentially you see that the channels have a theta 2. So again, the sediment tends to be predominantly in the channel, goes inside, but predominantly it's here. The core of the wetland really sees all these surfactants and this lighter material, and the water is something in between. The other interesting thing from a connectivity perspective is when does this flux start going into the wetland? It's very different. The point at which they're connected is very different from the sediment for the water and for the surfactants. So this is, it's essentially giving us a chance to do fluvially transported material in a modeling framework that allows you, by changing one parameter, to mimic the, kind of mimic the physics of other fluvially transported materials. I'm going to go to my I'm going to get to my conclusions. What do you think? Fair enough? So I'm skipping all the third part, which is on sea level and subsidence, because it's late, because I talk a lot. So we're just going to get to the end. And so I started with this, fairly dramatic view and this conflict between stability and sustainability, which I think is very important to recognize. And I also made the argument that this is a conflict of scales, which I think affects the way we do analysis. And so remember that landscapes can be sustainable at one scale, but actually that's not representative. Can be sustainable at global scales, but may not be representative of what's happening at local scales, right? And at the same time, our interventions are often local, but they don't account for the fact that some processes like avulsions are very much global. And so I think these, leveraging this combination of modeling, field, and remote sensing, and I showed a bunch of remote sensing and modeling, but there's of course field observations behind, because otherwise you can't validate anything. I think this really helps in understanding network dynamics, in understanding the flux partitioning, and I think if we want to think about solutions to achieve landscape sustainability in terms of looking at future climate scenarios, this is all information. I think this gap of scales needs to be bridged, and I think we do have the information to do that. I'm going to stop. Thank you very much.